Hi there, welcome to Math 8, Unit 2, Lesson 1 on projecting and scaling. And so today we're going to begin by exploring scaling. And one of the things you'll be talking about or talked about in your class today was the idea of a dilation. And so we'll be focusing on that today as we talk about how one shape can be dilated to become a different shape, rectangle to rectangle. And we'll be talking about perhaps using a center in order to make that happen, and we'll also be using terms like scale factor. So some of these things are a little bit of review from 7th grade, but just kind of taking a look at what they are. You began the lesson today with a number talk, remembering fraction division, and you had some questions here that asked you to divide things by 2, find its quotient, and write it as a fraction or mixed number. So just recall how to do that. If I want to turn this into an improper fraction, I can do 4 times 6, which is 24, and then I'm going to add 24 plus 1 to give me 25. So I can rewrite that mixed number as an improper fraction, 25 over 4. When I divide by a number, dividing by 2 is the same as multiplying by the reciprocal, which is 1 over 2. And now I can go straight across. 25 times 1 is 25. 4 times 2 is 8. Then I can either leave it as a fraction there, or I can put it in a mixed number. I prefer to go mixed, so 8 goes into 25, or I could say there are 3 8s inside of 25, because 8 times 3 is 24. 25 minus 24 is 1, so I have 1 left over, and my denominator stays the same. So I have 3 and 1/8, which, if you think about it, makes sense. If I have 6 and a fourth, and I'm cutting that in half, it means I have this. I have 1, 2, 3, 4, 5, 6, right? Those are my 6s. And if I have a quarter of something, let's just go ahead and draw a shape right here. If I have a quarter of something, it means I have this much, okay, of something. If I was to cut this in half, I would take 3 of them. So that's where the 3 comes from. And in terms of the 8th, if I was to take this quarter and cut the quarter into a half, right, a half of a quarter, then I end up with 8s, right? 1, 2, 3, 4, 5, 6, 7, 8. I cut that a bit, so I take that little bit there and add it to get an 8. Anyways, you did some more. Let's move on. Lesson part 2, sorting rectangles. It says that rectangles are made by cutting an 8.5 inch by 11 inch piece of paper in half again, and so on, as illustrated in the diagram. Find the lengths of each rectangle and enter them in the appropriate table. So you have all these lengths here for the rectangle, and we're chopping it in different pieces. Okay. So if I had, for an example, let's look at A. A is your big one, right? So A is given. Let's see how I do this here. Let's adjust this. Oops, sorry. If I have my rectangle A, and you have a chart you can look at as well, and I have my length, which is they call it the short side, and I have my length of the short and length of the long side. The length of the short side here on A is 8.5, and the length of the long side is 11. Okay. When I look down, if I want to find what they all are, B is going to be 8.5 on the long side. The short side's half of that. Half of 11 is going to be 5.5. That's the short side by the long side, 8.5. When I come over here, I'm cutting 8.5 into half. So half of 8.5 is going to be 4.25. And half of the long side here is still 5.5. That's my C. For D, I'm still the same length, 4.25, but now I'm going to be half of 5.5. Well, half of 5.5 is going to be 2 1/8. All right, no problem. So that 2 1/8 is the same over here for E, 2 1/8, but the length here is half of the 4 1/4. So 4 1/4, we would say that one gets chopped in half. A little tougher to do here. We're going to go with a 2 3/4. Again, you could do it doing the math way. We could go 4.5, and we could divide that by 2, which is part of your warm-up, right? And so when you do that, you get those answers there. So now if I take these numbers and I put them into my table, which is what it wants me to do next. It says some of the rectangles are scaled copies of the full sheet of paper and into the measurements of those. And so just doing the eyeball test, we could take a look here and say, well, which ones look like the same shape as the paper? We'd probably look at it, eyeball it, and say C looks pretty good and E looked pretty good. Okay, just in terms of how they look, just the eyeball test. So let's go ahead and add those lengths here. So C, the longest side on C was 4 1/4, you said, and the length of the short side was 4 1/4, and the long side was 5 1/2. And with the rectangle E, you had 2 1/8, and then you had 2 3/4. Okay, so the ones that were not scaled copies of the full sheet of paper, what you're left with is B and D. The short side of B was 5 1/2, with the long side being 8 1/2, and the short side of D was 2 3/4, and the long side was 4 1/4. It wants you to then look at the measurements of the rectangles that are scaled copies. So up here, what do you notice about the measurements of these rectangles? Look at the measurement for the rectangles that are not scaled. What do you notice about those ones? So when we're looking at the measurements here, what we can see is that in terms of the scale copy, which is really going down the column here, I am multiplying by 1/2, or dividing by 2 to go from one row to the next. 11 divided by 2, or multiplied by 1/2, gets me from one row to the next. That's what's happening there. If I was to go up this direction, we're multiplying by 2. Of course, that would be the reciprocal, right? So either I'm multiplying by 1/2 to go make it smaller, or multiplying by 2 to make it larger. Similar thing is happening here as well. Okay, to go down this direction, we are multiplying by 1/2. If I'm going to go up the other way and increase the size, then I'm multiplying by 2. So we have a scale factor of either 2 or 1/2, depending upon what we're doing with that shape. And you end up with a lot of equivalent ratios when you start playing with those numbers to see how do they relate to one another. When you take the rectangles in class and you stack them up to show the scale copies, you can notice that when you look at these things, the corners are what tend to line up. And so if you were to take a straight edge or a ruler and line up your corners here, you can draw a line from one corner to the next. And when this happens, it's a way of indicating, yep, we have some scaled copies of each other and they're proportional to each other as well. When I take the other two rectangles and I do the same thing for them, because they are proportional to each other, you have no problem recognizing that, yep, they fit there as well. And so it's kind of cool to look at the diagonal. The diagonal line is going to go through the vertices of each of these rectangles. Okay? And that happens because we're making a scale copy, and it works that way. This becomes important in a few lessons from now, and we'll start talking about doing the same dilation idea, but with a circular grid. All right? It's kind of fun. So wait for that in a couple days. If I stack all the rectangles largest to smallest so they all line up in a corner, compare what you drew. Can you tell which set they came from? Yep, you can tell. Now, what's interesting is if I take this rectangle here, I can actually make it fit right in here. I can make it fit in here. It's about that space there, and its vertices is going to match. This one as well, if I was to do this one, fits right about here, and its vertices is going to match. So you can actually place or layer this one inside of there, which is kind of neat. In terms of the Are You Ready for More, looking at some more scaled copies, he talks about a regular paper being 8.5 by 11, but in other countries they use millimeters, and they have 210 millimeters by 297 called A4 paper. Are those scaled copies? Well, to decide if it's a scaled copy, let's convert our millimeters into inches. It's good if you can do a little Google search if you wanted to, but in 1 inch is equivalent to 25.4 millimeters. So if I wanted to find out if the 210, how many inches are in 210, I want to find out how many inches there are in 210 millimeters, I could set up a little proportion like this, and if I cross multiply back and forth, essentially I'm going to move this guy to there. So you have 210 equals 25.4x. Divide both sides by 25.4. Kind of going the long way here for you. And when you do 210 divided by 25.4, you find out that you have 8.4 8.26 and a few other numbers. So just kind of chopping it off. So you have about an 8.26. So it's a little bit shorter than the 8.5 number, isn't it? They don't quite match. You could do the same thing for the length. So 25.4 equals x over 297. If you notice up here, all we ended up doing when we did the cross multiplication by moving the 210 there is we ended up with 210 over 25. 210 over 25 for my answer. So right now I'm going to do a little shortcut here and just do 297 divided by 25.4. Just moving it there and dividing right away. So 297 divided by 25.4 ends up being 11.69 for the value of my other x. So those become the lengths in inches for those millimeters when you convert them. So they're not proportional. All right, so then you had an optional activity which you might have done. Not sure if you did this or not, but if you did, this was an optional one your teacher may have elected to do. And you have a picture of a rectangle, and it talks about this rectangle being divided into smaller rectangles, and then you have smaller ones labeled B and even smaller ones labeled C. And so when we look at what's happening, is B a scaled copy of R? So is this one here a scaled copy of the larger one? We would say yes, and in terms of what the scale factor is, if the length of R is 1, right, we're breaking it down so that now this becomes 1, 2. There's 2 of those to fit inside that 1. So our scale factor means I'm actually reducing this by a half. So I'm cutting it into a half in terms of the length. This length is half of the original, and this length is also half of the original. So it's a scale factor of a half. For the C part, C, because it's fitting inside of here nicely, is also a scaled copy of B. And in terms of what it's going to be, we can see that there are 1, 2, 3, 1, 2, 3 fitting in a space that normally was just the 1. So it's a 1 to 3 type of scale factor. The original was 1 and the new one is 3. Taking that information then, if this is a scaled copy of B scaled of R, C is scaled of B, we could also say C is scaled of R as well. We would say yes, and in terms of what the scale factor is going to be, if I was to continue this drawing along this line here and do this, we can see I have 1, 2, 3, 4, 5, 6 fitting inside of what used to be 1. So we could say that my scale copy here is 1 to 6. All right, so scale copies of the summary of rectangles have an interesting property. And we can see that what that property is, we can see that the line goes to the vertices right there. So the larger rectangle is a scale copy of the smaller one with a scale factor of 3 over 2. Notice how the diagonal of the large rectangle contains the diagonal of the smaller rectangle. This is the case for any 2 scaled copies of a rectangle if we line them up as shown. If 2 rectangles are not scaled copies, then the diagonals do not match up. So if they're going to be a scaled copy, then the diagonals are going to match up and it's going to work just fine. Okay, let's take a look then at your homework for tonight. For tonight's homework, you began by doing some comparisons here. It said you started with rectangle A measuring 12 by 3, and B's a scaled copy of A. Select all the measurement pairs that could be the dimensions of B. All right, so let's set it up this way. We could set them up as a proportion. Okay, let's look at A first of all. I have 12 to 3 is my first, my given, right? 12 to 3 is what I have, my dimensions there. If I set that equal to 6 to 1.5 and cross multiply, use cross products, I can see if this is going to be proportional or not. I could also do the eyeball test too and say, well, to go from 12 to 6 is multiplying by, is dividing by 2, right? Dividing by 2 or multiplying by a half. If I do 3 times a half, what's half of 3? It's 1.5. So we'd say, yep, A is going to work, no problem. For B, set it up again, 12 to 3, and here I have 10 to 2. I can cross multiply and I have 24, and over here I have 30. Those are not equal, so B is not going to work. I'm going to take a look at C. I have 12 to 3 again, set it equal to 13 to 4, And 12 times 4 is 48. And then 3 times 13 is 39. Those are not equal, so C is not going to work. For D, we have 12 over 3 equal to 18 over 4.5. That's a fun little number to play with, isn't it? But when you multiply this out, 12 times 4.5 is 54. 18 times 3 is 54. Those are equal, so we would say they're proportional, and it's a scaled copy. And finally with E, 12 over 3, setting it equal to 80 over 20. You can eliminate the zeros there. And 2 times 12 is 24, or if you want to think 240, you can. And 80 times 3 is 240. That's going to work, so E works as well. So set them up as a proportion, use cross products and multiply to see if it's going to be a scaled copy. All right, number 2. This one you need to be careful on the order in which you do things. It says rectangle A has a length of 12 and 8, and B has a length of 15 and 10. Rectangle C has a length of 30 and 15. Okay, so what they're saying is that if you have a length and a width for rectangles A, B, and C, we can set up a little table like this, and we can say A is 12 by 8, B is 15 by 10, and C is 30 by 15. So just looking at things, we can start to kind of get an idea is, are there some proportional relationships here? Are there some scale factor and things happening? These are larger numbers, so it's hard to tell right away. I could look quickly and say, well, 15 times 2 is 30, 10 times 2 is 20. So I automatically can look and just visually see before I even look at questions that I don't have a scaled copy between B and C. When I look at A and C, it's a little trickier because these are not numbers that I'm comfortable using all the time, so it's hard to say. Are they scaled copies? Are they not? I'm not really sure, right? So let's look over here. So there's another way of looking at this problem and solving it. Let's read the A choice. It says, is rectangle A a scaled copy of rectangle B? Okay, so it's asking if A is a scaled copy of B. So my original one is actually going to be B that we're dealing with here. And I'm going to take the original and I'm going to multiply it by a scaled factor in order to find out my copy, the size of my copy. That's essentially what we're doing here in this setup. We have the original times a scale factor is going to then give me my copy value. So looking at rectangle A, let's just take one length at a time here, okay? So we begin with our original value of B. Now for B, because it's B here, so we're looking about B times the scale factor is going to equal A. That's what we're trying to figure out. For B, let's look at the width. We had a width of 10. Okay, my 10 is going to be multiplied by a scale factor, which we don't know, and we want to see if it's equal to the width of A, 8. All right. So to find out what value goes in there, if I was to put an X in here, for example, what we're trying to figure out, I could divide both sides by 10, and X is equal to 8 over 10, which can be reduced to 4/5. All right, so we have a 4/5 there to help us know that that is going to be the scaled factor for 4/5. Does that work with the length as well? That's the way we're going to check this out. Is 15 times 4/5 equal to 12? Well, if I reduce here, that becomes 1 and a 3, and 3 times 4 is 12. So yes, it worked. So we started with the width and found that the width was proportional and has a scale factor of 4/5. We used the scale factor for the length and confirmed that it was true. So we would definitely say yes for A. Looking at B. B says, is rectangle B a scaled copy of A? So we're asking it this way. I take A, multiply by a scale factor, and I get to B. Does that work? Well, we'll do it the other way now. Let's start with A's width. We have 8 times a scale factor is going to equal 10. If I divide both sides by 8, divide both sides by 8, my scale factor is going to be 5 over 4, right? 10 over 8 reduces to 5 over 4. Let's use this number to see if it works for the length, okay? So if it works for length, we would say that 12 times 5 over 4 should be equal to 15. 4 goes into 12 3 times, and 3 times 5 is 15. So we can say yes, it's going to work as well. For C, explain how you know that rectangle C is not a scaled copy of rectangle B. Well, for me, when I look at this, what I said before is I noticed that the length doubles times 2, but the width does not double. It is not times 2. Because those scaled factors are different, this is not going to be a scaled copy. You need to write that down in your words, though, okay? And D, is rectangle A a scaled copy of rectangle C? And if so, what's the scale factor? So is the scale factor to go from 12 to 30, 8 to 15? Well, that's a great question. Well, if it's a scaled copy, then the length of one and the width, so the length and the width, should be proportional to the length and width of the other, 30 over 15. When you do this, we could also then reduce 12 over 8 can be reduced into 4 goes in here 3 times, 4 goes in here 2 times. This one, 5 goes into there 6 times, and 5 goes in here 3 times. I can keep reducing. 3 goes in there 2 times, and 3 goes in here 1 time. So is 3 over 2 equal to 2 over 1? I'm going to probably go with no, but we can double check. 2 times 2 is 4. 3 times 1 is 3. Those are not equal. So we would say that A and C are not scaled factors or scaled copies, so there is no scale factor there. Okay, looking at number 3. Number 3, you're given several shapes, A, B, and C, and we're going to have to do some things with them. Okay, first with A, it wants you to draw a scaled copy of polygon A with a scale factor of 1/2. Okay, to do this here today, what you're going to need to do is you're going to need to measure this length, measure the length, and then you're going to cut it in half, divide it by 2. It depends on your book, okay? I have a photocopy of the book, so mine might be a little different than yours, so be careful there. So for me, I might look at this and count centimeters and recognize that I have, well, I can even look at millimeters. I actually have 30, and I have 35, 36, 37 millimeters, hard to say. We could probably say 36. Let's go with 36 millimeters because it's an even number. Again, I'm just estimating here for now. If that's 36 millimeters, I could look over here and think that this might be maybe I say it's 22 millimeters. So if that's the case, half, so 36 times 1 over 2 is going to be a length of 18 millimeters to make the scale factor of half, and my 22 millimeters times 1/2 is going to be 11 millimeters. So then I would need to draw that out to draw a line of 18. So there's 10 to 18, and then draw a length here of 11. I want to get a nice right angle there if I can, and make the length of 11 to there, and then we'll connect the dots between my 2 points. Because the triangle, I don't really need to worry about drawing or measuring it as a length. And there's my scaled copy of polygon A. That's a factor of 1/2, so it's half the size. For B, and B is going to ask us to make a copy of B with a scale factor of 2. So we're going to take this and multiply all the lengths by 2. One of the things I want to start off doing first of all is I'm going to make a copy of, I'll make it on an edge here, make a copy of this angle right there. Copy of that. So this is my bottom, and I'll make a copy of that guy, and a copy of that guy, because when I do a shape, even though my lengths can change, my angles need to stay the same, don't they? So if I'm going to do this at a scale factor of times 2, I need to measure the original one and see how long was it originally. And for this one here, I'm just going to estimate this is about 2.5, okay, 2.5 centimeters long that way. It's about same on this one, 2.5 here, 2.5, 2.5. This length here, just measuring on again, this is my copy, yours might be different. It's a little less than 3, but just for the sake of our picture and drawing, I'm going to call it 3 and 3. So to make this work, I need to have an angle down below here. So here's my angle down here. I'm going to go ahead and just trace over this angle measurement and go like this. See if we can see that guy in there. Not really. So let's go like this. When I do that, I have my angle pops up. That's my angle on the bottom. And because we're doing it times 2, that means instead of 2.5, I'm going to multiply that by 2, so I end up with 5 as my length. So I'll start here at 5. We're going to go out to the end. And over here we have 5, so we'll follow my little line. And we'll go out to the end. My next angle measurement here, I need to see if I have this angle correct. So I can flip this over right there, draw my guy there, and make my little hash mark right there, which tells me which way I'm going to start going there. And make one here, which tells me the direction I'm going to go. And 3 times 2 is 6, so I'll come out here 6 centimeters. It's about there. And if we did this right, we should get pretty close. Here's 6. Oops, not quite. 6 gets me to there. So one of my angle measurements is off. Looks like that one's off a little bit. Let's see if I was to go here to here. Is it closer? It's closer. Not perfect, but you get the idea. I should have something. Boy, that's really bad. Sorry. Should be something more like here to here, where this is 6 and 6 and 5 and 5. All right, not perfect. Not a lot of space there either to work with. That's okay. For C, they want you to do a scale factor of 1/4. So again, the same idea. If you think of it this way, if this is half of the length there, I'm going to then cut this in a half there. Okay, so I'm cutting that in half. So here's a 1/4. If I cut this in a half, and then I cut in halves here, a 1/4 is going to be just this itty bit right here. Okay, so a 1/4 would end up being this space right there as a 1/4. That's my 1/4 scale right there. So I'll let you draw that one. I get you close, okay? Looking at the next one. We have, which of these sets of angle measurements could be 3 angles in a triangle? Angles in a triangle need to add up to what number, do you recall? 180 degrees. Has to equal that. So when I add these together, I need to add them up and say which one equals 180 degrees. Here we have 150 degrees. Here we have 180 degrees. Here we have 210 degrees. And here we have 240 degrees. So it's really just a question of, can you add 3 numbers together? And do you know which one is 180? Hope so. There we go. Okay, in picture AB, and you have lines AB and CD are parallel lines, and we have a transversal running across there as well. And so we want to find some different angle measurements. Okay, so this is my transversal. First I have parallel lines. I like to go like this, parallel lines there. I have my transversal, which is running this way right there. It's kind of cool information. And the questions I'm being asked to do here is they want to know the measurement of angle B, C, and D. They want to know the measurement of angle E, C, and F, and the measurement of angle D, C, F. So let's do these one at a time. So first of all, they want to know BCD right here, this angle measurement. This angle measurement should be equal to this angle measurement right here. And the reason for that is, if you recall, that's a 38, sorry. These are what we call our alternate, because they're alternating the sides of the transversal. Interior, because they're both inside the parallel lines. Angles. These are alternate interior angles. So this is going to be a 38 degree angle right there. Next one, ECF, is right here. ECF is across from BCD. It's going to be the same angle measurement because it is a vertical angle. Alright, so we're good there. This is 38 degrees. And the last one is DCF, is this measurement here. And this measurement, if you add it to the 38, is going to be a supplementary angle altogether for 180. So that means we take 180 and we subtract 38, and 180 minus 38 is going to be 142 degrees. And that is because it is supplementary. Okay, so this is 142 degrees. All right, and that's all you had to do. Good luck on your next assignment.